Good afternoon, everyone. This is the path planning walkthrough. What we're going to cover today is how to build your path planning project. So there's a few basic things we want to go through. First thing is the project overview. So we go through the rubric and I show you a demonstration as well of how the project should perform. Next thing is the high level design. So where this fits into the architecture of a self-driving car and what is involved in, or what steps are involved in building a path planner. And then finally, I want to work through the steps for implementation. So once you understand the high level architecture, now you choose the architecture you want to use, and I'll show you an example that I've implemented for the project. Then I want to walk through the code, some samples of code to show you the steps for implementation. And then we'll have a Q&A afterwards to go through any questions you might have. Again, you can ask any questions as we go through the session. Um, okay, so let's get into it. So the rubric for the car involves a number of basic requirements. So it's a circular track. You want to navigate the car around the track, and while you're doing that, there's a few basic things you want to do. You want to stay on the road, so you can't wander off the road at any point in time. So obviously you need to know where exactly the road is and where all the lanes within the road are as well. You need to stay within the lanes. So obviously, if you're doing a lane change, there's a lane transition, but you can't stay on a lane line. You want to stay within. You want to establish yourself within a very short period of time in a specific lane. You want to obey and stay close to the speed limit. So, in essence, you want to go as fast as possible as long as you don't go above the speed limit. And then at the same time, you want to avoid colliding with any traffic. Obviously, if you're staying within the speed limit, if there's slower traffic, optimally you want to avoid tailing slower traffic if you possibly can. So you want to go as fast as possible, as long as it's under the speed limit. You want to avoid colliding with any traffic on the road, so which means you have to know exactly where traffic is and will be in the future. And then finally, you want to keep passengers comfortable. So you want this to be almost as realistic as possible, which means that the car can't be jerk accelerating or swerving or making any sudden moves that are absolutely unnecessary to executing a successful path. So the first thing we're going to do is we're going to walk through a demonstration of what this would look like. So let's just go, I'm going to switch over to my project. I'm going to fire up the path planner and the simulator, and then just show you exactly what the project should look like in production. So here's the path planner. You set how far ahead you're going to plan your trajectories. And then the car, as it approaches traffic, it has to make a decision. If the traffic is slower than the car is going, it has to make changes in lanes, such as what happened just now. The car, obviously, in this case, decided it's going to switch to the leftmost lane because that seems to be the optimal path forward. Notice one of the things about my behavior planner in this case is that the car prefers to be in the center lane. So one of the decisions I made as part of the architecture was keep the car in the center lane because then it makes if you can stay in the center lane, perfect. If you have to make transitions between lanes, then it's just one lane change. You're not trying to execute multiple lane changes simultaneously. So it always tries to stay in the center lane, except in cases when it needs to overtake, in which case it will then switch lanes, as you're seeing here happening right now. And you'll notice as well, like all the lane transitions are pretty smooth, so there's no jerk acceleration. You should not see any red flags appearing on the simulator. So every transition you make should be smooth enough that the level of acceleration is within the tolerances set for the project. And then your ideal is that you are actually able to go around the entire track without any incident. So that's without going off the road, without colliding with any traffic, without exceeding the jerk acceleration limits. All right, so this is give you a sense of how what the car should look like in your actual project. So you again switches back to the center lane. Okay, so what you see on the left-hand side here, this is just debugging that I implemented as part of my project. As I was going through trying to figure out why things were not working correctly, I actually dumped a lot of information to the console. I actually dumped it to a text file log as well, so I can review it afterwards to try to get a sense of when something goes wrong, what exactly happened at a point in time. So you'll see a lot of things in here. You'll see like what decision was made. So we'll go through this as we're going through the code, but what decision was made. The decision is what state is going to be actually implemented and the cost of that particular state. And then it's actually going through each of the states and then figuring out the cost for each one of those states as well to be able to make the decision as to what's going to be done next. So this is just my way of helping to decide what is going right, what is going wrong as I was building out the code. You don't have to take this approach, but this one worked really well for me. Okay, so that's the demonstration. So Uh, as far as the design is concerned, so this is the general architecture for a self-driving car. For this particular project, you're going to be fed all the sensor information, all the sensor fusion is going to be done on your behalf. The map is going to be provided to you as well. You don't have to worry about traffic lights or anything like that. All you have to focus on is the planning aspect. So the control is going to be done on your behalf as well. The only thing you have to focus on is the planning aspect. So for the planning, there's a few components that are built into it. I'll tell you a trick I use as part of my design. You can decide whether you want to do that or you want to make yours a little bit more robust design. But so there's a few basic pieces involved are obviously you have to digest a map. There's a set of waypoints designed yeah, smoothly across the track. You have to digest a map and be able to use that map to localize the car and then decide and set your path, your trajectories that you generate based on your current location, based on where you want to be in the future. That involves all that information in relation to the speed you want to be at, the acceleration you want to be at, the lane you want to be in as well. You have to you can design a route planner that makes a decision based on the layout of everything that's on the track of which is the optimal route to take forward. So you can use A-star search or some other algorithm to design a route planner. The trick I use as part of my implementation, which actually worked very well, is I did not use a route planner. Since it's a circular track, I used a very, very basic implementation that just simply reacts to traffic predictions and then the behavior planner, based on the cost functions that are defined in the behavior planner, makes a decision of what's the best lane to be in. Because you're going around a circular track, your only real constraint there is traffic. So you have to react to traffic, but you don't have to be able to decide. Am I going to turn left onto another road? I'm going to turn right onto another road. Do I need to keep straight? Whatever the case may be, you're always keeping straight. The one drawback of this method, and I think it's partly because I decided to only look at traffic within a certain range of the vehicle. So I didn't look at all traffic, I just looked at traffic in what I call the plan ahead range. The only drawback of that method is that in some cases you get stuck behind slower moving traffic because the decision for the car was, well, I'm going to just switch to one lane, the left lane, when there's another lane they could have chosen, the right lane they could have chosen as well. But that occurs very rarely, and the only drawback of that is you're going to be running slow until that you're able to clear that traffic. So that's a route planner. That's one part you can implement. The prediction is basically you don't want to look at traffic where it is right now. You want to look at traffic for where it's going to be in the future to line up your future trajectory state to the state of your traffic. So there's a number of different things you need to look at in there to be able to decide where the where the traffic is going to be in that future time horizon. And in the behavior planner, we're going to walk through that as well. That is basically deciding which lane do I want to be in, how fast do I need to go, can I actually make a lane change, and so on. Okay, so let's go through the steps to implementation, and then we're gonna walk through the code. So first thing, localize the vehicle. You need to figure out exactly where the vehicle is, so you need to know exactly what you need to react to around you, surrounding you. So it's in terms of lane, in terms of actual waypoint, closest waypoints to the vehicle as well. Second is predict the future state of traffic on a specific time horizon. Again, you set that time horizon based on how far ahead you want to predict your trajectory and what is comfortable for being able to react without having jerk acceleration. Decide on the desired states of the vehicle. So when you're defining a state machine for your behavior planner, you need to decide on your states, the desired states for the vehicle. So I initially started out with several states and then eliminated a few of those very quickly because I didn't really need them, especially in because of the way the cost function was designed. Then you create a trajectory planner to obey the constraints on speed and acceleration. Then you're going to create a cost function to guide state transitions in the behavior planner. Now, basically, will compose your behavior planner, and then you're going to integrate these items sequentially. So you're going to basically, as you go through this process, you don't want to have to build out every single thing and then test it all together. Then it's hard to figure out which part is at fault. So you integrate them sequentially until you have your full path planner implemented. So let's walk through some code samples to give you a sense of what this will look like in in your code base. And so let's start at the main function, and this gives you a very high level overview of the actual operation of the behavior planner. So there's a lot of this code is provided beforehand, but what I decided as far as the architecture is concerned was to divide the implementation into a few basic objects and delegate responsibilities to those basic objects. So the objects were trajectory planner, which is actually going to decide on trajectories. So it's just very dumb. All it knows is here's what the desired outcome is, and I want to design a path within constraints to meet that desired outcome. The smarts really lies with the behavior planner that makes those decisions on the state transitions. So it calls to the behavior planner, so the trajectory planner, whenever it needs to make a decision about whether a particular transition, but whether a particular path is viable and which is the most viable path. And then finally, trajectory just manages, it basically tracks the current trajectory because like if you've already planned a successful trajectory, typically what you want to do is if it still works, you want to just extend it. If it doesn't work anymore, you're going to cut it short and you start a new trajectory. So the trajectory object or class tracks trajectories in the actual vehicle. So that's one part. The second thing is this is just consuming all of the map data. So you load the map data. This is all provided code. You load the map data, and you can actually provide a way to be able to consume it from all those different objects within the architecture. I